Hello there. Welcome back to Midnight Ocean. I'm Velen, your guide to traveling through the wonders of the ocean. Tonight, we're going to navigate through the most inexplicable phenomena of the oceans. If these cozy moments calm you, I invite you to subscribe, share a comment, or leave a like. Now, get comfortable, take a deep breath. Don't be afraid, you're safe here. Let's dive deep into the sea and let our imagination guide us to a peaceful and deep night. The ocean covers 71% of the planet and still holds unanswered questions. Only 26% of the ocean floor had been mapped at high resolution as of 2024. This means most of the planet's underwater terrain, mountains, valleys, trenches, plains, remains invisible to science. Within this almost entirely unknown territory, some phenomena have been recorded, measured, captured on scientific instruments, and remain without a definitive explanation, even after decades of investigation. These aren't legends. They're real data picked up by U.S. Navy hydrophones, NASA satellites, sensors on oil platforms, and research equipment on the seafloor. Phenomena that resist simple explanations. Imagine trying to know an entire continent's surface while only seeing a quarter of it clearly. The rest would appear as blurry smudges, shadows without defined outlines. That's exactly the situation with the ocean floor. Ship sonars trace only specific routes, leaving enormous gaps between one pass and another. Satellites help estimate terrain through subtle variations in the water's surface. But this technique delivers low resolution, unable to reveal formations smaller than dozens of kilometers. Mapping the rest would require additional decades of expeditions, according to estimates from oceanographers involved in international bathymetric mapping projects, such as Seabed 2030. Extreme depth makes direct exploration difficult. Regions below 6,000 meters experience pressures equivalent to hundreds of atmospheres, crushing any structure that isn't properly reinforced. Manned submersible vehicles, like the Alvin operated by American institutions, reach only fractions of this total territory. Autonomous robots extend the range, but limited power and restricted communication impose severe limits on missions. Every additional meter of depth represents a growing technical challenge, raising the costs and risks of any scientific expedition dedicated to uncovering this hostile, remote environment. Permanent darkness characterizes most of this ocean volume. Sunlight penetrates only down to roughly 1,000 meters. Below that, absolute darkness reigns continuously. Organisms living at these depths have developed extraordinary adaptations. Their own bioluminescence, heightened tactile sensitivity, extremely slow metabolism suited to scarce resources. Scientists regularly discover new species during one-off expeditions, suggesting biodiversity is vastly underestimated. Every dive reveals creatures never before cataloged, reinforcing the notion that current knowledge represents a minimal fraction of the real life that actually exists in this submerged realm. Acoustic instruments have become an essential tool for investigating regions inaccessible to the eye. Hydrophones, specialized underwater microphones, pick up sound vibrations traveling through water, a medium that carries sound far more efficiently than air does. A hydrophone network originally installed for military purposes, monitoring submarines during a past period of geopolitical tension, was later made available for civilian scientific research. This infrastructure made it possible to detect sounds never cataloged before, some attributable to known geological phenomena, others whose origin remains definitively unexplained. Underwater sounds travel surprising distances due to the unique physical properties of water as a propagation medium. Differences in temperature and salinity create layers that channel sound waves horizontally across thousands of kilometers without significant dissipation. This phenomenon, known as the SOFAR channel, allows relatively modest sounds to be detected at distances that would seem impossible in the atmosphere. Whales exploit this mechanism for long-distance communication. Military engineers harness the same principle to track submarines. Civilian scientists later inherited the ability to monitor entire oceans using just a few strategically positioned sensors. Cataloging ocean sounds has become its own scientific discipline, combining acoustics, marine geology, and biology. Researchers compare captured patterns against extensive libraries of known sounds. Underwater earthquakes, volcanic activity, glacier movement, vocalizations from various marine mammals. When a sound doesn't match any catalog pattern, it becomes a priority subject of investigation. These cases, though rare, spark extensive academic debate, multiple competing hypotheses, and occasionally a definitive resolution after years of analysis. Other times, explanations remain partial, accepted provisionally until additional evidence emerges. International pressure to explore and map the oceans has intensified over recent decades, driven by combined scientific, economic, and environmental interests. Understanding deep ocean currents helps model global climate more precisely. Identifying mineral resources on the ocean floor interests various industries. Protecting fragile ecosystems requires detailed knowledge of habitats not yet documented. Collaborative international projects, bringing together dozens of countries, have committed to mapping growing stretches of the ocean floor. Though progress remains slower than the scientific community, eager for answers, would like. Emerging technologies promise to speed up this mapping effort in the coming decades. Autonomous underwater drones, equipped with artificial intelligence capable of navigating independently, reduce the need for constant human oversight. Miniaturized sensors, cheaper and more durable, allow for deployment at a larger scale. Next-generation satellites offer increasing resolution for indirect estimates of underwater terrain. Despite these advances, the scale of the challenge remains monumental, equivalent to mapping in detail a surface larger than all of Earth's continents combined, situated in a hostile, opaque, and deeply unknown environment. While mapping advances gradually, phenomena recorded decades ago continue to be re-examined in light of new data and improved technology. Sounds captured in the 90s, for example, remain archived in databases accessible to today's researchers, who apply modern spectral analysis algorithms to extract information that was previously imperceptible. Each reanalysis can confirm earlier hypotheses or reveal nuances originally overlooked. This ongoing process of scientific review characterizes serious investigation into territory that remains largely unexplored, where definitive answers stay conditioned on the evidence available at each point in history. The bloop, the loudest sound ever recorded in the ocean. In 1997, hydrophones belonging to the American Oceanic Agency NOAA, installed to monitor seismic activity in the South Pacific, picked up an ultra-low frequency sound so powerful it was detected by sensors spread more than 5,000 kilometers apart from each other. It was louder than a blue whale's call, and unlike any known marine creature. The sound was named the bloop. NOAA researchers suspect the hydrophones picked up the sound of a large Antarctic iceberg colliding with the seafloor. That's the most widely accepted explanation today. But the event was never directly observed, and the correlation between the bloop's acoustic pattern and known ice-fracturing sounds remains a subject of debate among marine acousticians. The equipment responsible for capturing this sound was part of a system originally designed for military purposes during a period of intensive underwater surveillance. Hydrophones strategically distributed across the Pacific allowed for tracking submerged vessel movement through specific acoustic signatures. After being redirected towards scientific use, these same sensors began recording various natural phenomena, from underwater earthquakes to the vocalizations of large cetaceans. In August 1997, during routine monitoring operations, the system captured a completely unprecedented sound pattern, setting off alarm bells among researchers used to cataloging already known sounds from the regional marine environment. The bloop's intensity impressed scientists from the very first analysis. Sounds capable of traveling such great distances through the ocean normally require extraordinarily powerful sources. Blue whale vocalizations, considered among the loudest biological sounds on the planet, reach significant intensities but still fall short of the one recorded here. A direct comparison between the two phenomena revealed a substantial difference in magnitude, quickly ruling out the hypothesis of a conventional biological origin. This initial finding heightened scientific curiosity, leading researchers to consider alternative explanations involving geological processes or, speculatively, creatures not yet cataloged by science. The sound's spectral pattern showed distinctive characteristics. Frequency analyses revealed a unique signature that didn't precisely match any existing catalog of known geological or biological sounds at the time. This singularity fueled various speculations, some suggesting the remote possibility of a giant marine organism unknown to science. A hypothesis quickly dismissed by marine biology experts, who argued there was no anatomical or ecological evidence supporting the existence of a creature capable of producing such sound intensity. Serious scientific debate then focused on non-biological physical mechanisms capable of generating such a particular acoustic signature. The iceberg hypothesis gained traction progressively as researchers correlated temporal patterns. Fractures in Antarctic ice masses, especially during calving events or collisions with the ocean floor, can generate intense low-frequency sounds through physical processes well documented in other instances. Internal stresses built up within massive ice structures, when released abruptly, produce low-frequency sound waves capable of traveling extensively through the SOFAR channel. Glaciologists contributed specialized knowledge, suggesting a plausible mechanism consistent with the general characteristics observed in the bloop. The approximate geographic location of the source, calculated through triangulation between multiple hydrophones, was situated in a region consistent with known Antarctic glacial activity. This spatial correlation reinforced the iceberg hypothesis, though precise determination remained limited by the distance between sensors and the complexity of sound propagation in a three-dimensional ocean environment. Researchers acknowledge that acoustic triangulation on such a vast scale carries considerable margins of error, especially when dealing with sounds whose origin and mechanism are not yet fully understood by the scientific community specializing in underwater acoustics. Similar events, though less intense, were later documented in Antarctic regions where direct monitoring of glacial fractures could be correlated with simultaneous acoustic capture. These subsequent observations provided additional support for the geological hypothesis, demonstrating that the proposed mechanism was physically plausible and reproducible under natural conditions. However, none of these later events reproduced the exact intensity or spectral signature identical to the original bloop, leaving an element of uncertainty as to whether the accepted explanation perfectly matches the phenomenon specifically recorded in 1997. The marine acoustics community remains divided on whether to consider the case definitively closed. A significant portion of researchers accept the glacial explanation as satisfactory, sufficiently supported by indirect evidence and known physical mechanisms. Another segment maintains methodological reservations, pointing to the absence of direct observation of the causal event as a relevant gap in any rigorous scientific reconstruction. This disagreement, while not involving any dispute over the raw captured data, reflects legitimate differences regarding what counts as sufficient evidence to close the book on a singular acoustic phenomenon that hasn't been repeated since. Public interest in the bloop spread well beyond specialized scientific circles, reaching popular culture through references in TV shows, mainstream articles, and speculative online discussions. This widespread interest, while beneficial for science communication, also generated considerable distortion, including baseless associations with mythological or fictional creatures that have absolutely no grounding in real evidence. NOAA researchers, in subsequent statements, repeatedly worked to clarify that the available data consistently points to a geological origin, with no legitimate scientific indication of exotic or unknown biological involvement. The bloop's audio recording remains publicly available through oceanographic databases, allowing contemporary researchers to apply modern analytical tools to that historical record. Signal processing techniques developed since then make it possible to extract spectral details that were previously inaccessible, contributing to the ongoing refinement of explanatory hypotheses. This reanalysis process illustrates how scientific investigation remains active even decades after the original event, incorporating technological advances to deepen understanding of acoustic phenomena whose origin, while largely settled, still holds nuances worthy of continued scientific examination. Julia, the voice that echoed thousands of kilometers in 1999. 2 years after the bloop, the same hydrophones picked up another sound, a long, almost human moan named Julia. It was picked up in the equatorial Pacific region, and although some attribute the sound to ice activity, its strange tone seems almost sentient. The sound lasted nearly a minute, too long for a simple fracture. Researchers suspect the hydrophones picked up the sound of a large Antarctic iceberg colliding with the seafloor. The ice hypothesis is the most solid one available, but the sound's duration and its location, far from the zones where Antarctic icebergs typically drift, keep part of the scientific community cautious about considering the case definitively resolved. The detection occurred through the same sensor network responsible for capturing the bloop 2 years earlier, showing continuity in the acoustic ocean monitoring maintained by American scientific institutions. A team of researchers, already familiar with analytical protocols developed during the investigation of the earlier case, applied a similar methodology to examine this new recording. Immediate comparisons between the two events revealed structural similarities in the sound signature, but also notable differences in duration and temporal pattern, suggesting a possible mechanistic connection without a complete identity match between the causal phenomena. The sound's almost vocal quality particularly intrigued the acoustic analysts involved in the initial investigation. Unlike the abrupt fractures typical of simple glacial events, Julia's sound pattern showed continuous modulation, drawing an informal comparison to a prolonged organic vocalization. Experts clarified that this perception, while understandable from a human perceptual standpoint, doesn't necessarily imply a biological origin. Complex geological sounds, especially those involving progressive sliding and fracturing of extensive ice masses, can produce temporal patterns that sound organically continuous without any connection to living organisms. Its roughly 1-minute duration set Julia significantly apart from previously documented glacial events, which typically show shorter sound peaks followed by rapid decay. This time span led researchers to consider mechanisms involving gradual, sustained processes, such as a mass of ice continuously sliding over an irregular seafloor surface, generating prolonged friction capable of producing a long-lasting sound. Physical models developed later sought to mathematically replicate conditions capable of sustaining acoustic emission over an interval so extended compared to similar previously cataloged events. The geographic location proved to be a particularly intriguing aspect of the case. Acoustic triangulation placed the sound's approximate origin in the equatorial Pacific region, significantly far from the zones where Antarctic iceberg drift is documented to occur with any frequency. This geographic discrepancy raised legitimate questions about whether the standard glacial hypothesis fit, leading some researchers to propose alternative explanations involving, possibly, an ice fragment that had drifted exceptionally far to lower latitudes before colliding with or fracturing near the seafloor in this atypical region. Researchers specializing in ocean currents contributed additional perspective, noting that Antarctic circulation patterns occasionally carry substantial glacial fragments much farther than would typically be expected, though such events remain statistically uncommon. This possibility, while not directly proven for Julia's specific case, offered a plausible path to reconcile the glacial hypothesis with the recorded atypical geographic location. Even so, the lack of visual confirmation or direct glaciological monitoring in the exact region kept a persistent element of uncertainty around this proposed reconstruction. Comparative spectral analyses between the Bloop and Julia revealed that, despite a potentially similar general mechanism, the specific signatures differed enough to rule out the hypothesis of an identical source or perfectly replicated process. This distinction suggested to researchers that the broader category of acoustic phenomena tied to glacial activity may involve considerable variability, depending on factors such as the size of the fragment involved, its speed of movement, the seafloor topography at the point of impact, and the specific temperature and salinity conditions of the surrounding water at that moment. Academic debate over Julia, much like with the Bloop, remains divided between accepting the glacial explanation as sufficiently solid and maintaining methodological skepticism due to the lack of direct confirmation. More cautious researchers argue that the imperfect geographic correlation and the sound's atypical duration justify treating the case as partially resolved rather than definitively closed. Others consider that known physical mechanisms, combined with the possibility of atypical glacial drift, offer a sufficiently parsimonious explanation, removing the need for additional untestable hypotheses. Relevant historical context includes the period of intensified Antarctic climate monitoring during the late 90s, when growing concerns over glacial melting drove greater scientific attention toward polar ice dynamics. This expanded interest generated more comparative data available for correlating acoustic events like Julia with independent observations of glacial activity documented through other methods, including satellite imagery and scientific expeditions specifically dedicated to monitoring the behavior of rapidly changing Antarctic glaciers. Julia's sound recording, preserved alongside the Bloop's archive in publicly accessible oceanographic databases, remains available for reanalysis by researchers interested in applying contemporary analytical techniques. Each new generation of computational tools allows additional nuances to be extracted from these historical records, gradually refining the understanding of the physical mechanisms involved. This ongoing investigative process demonstrates how ocean acoustic phenomena, even when largely explained, remain a subject of legitimate scientific curiosity, fueling questions about how many other sounds still await capture and analysis in the vast regions of the ocean that remain unexplored. Milky seas, stretches of ocean that glow for months at a time. Sailors have reported for centuries stretches of ocean that glow white at night, spanning areas that can cover tens of thousands of square kilometers for days or weeks at a stretch. The phenomenon is called milky seas. Although such emissions can't be fully reconciled with the known characteristics of any light-emitting organism, these so-called milky seas are hypothesized to be manifestations of unusually strong bioluminescence produced by colonies of bacteria associated with a microalgae bloom on the water's surface. Due to their fleeting nature and the scarcity of scientific observations, an explanation for milky seas remained undefined for a long time. In 2019, The crew of the sailing vessel Ganesha traveled through one of these events near Java, Indonesia, and photographed the phenomenon for the first time from sea level. A comprehensive database of Milky Sea sightings was published in 2025, an important first step toward understanding the phenomenon's climatology. The exact mechanism that causes bioluminescent bacteria to cluster together on a scale visible from space remains without a complete explanation. Historical accounts of this phenomenon date back to the logbooks of European navigators from the 17th and 18th centuries, describing oceanic expanses that appeared covered in snow or spilled milk, visible even under faint moonlight. Experienced crews recorded the event as a memorable anomaly, distinct from common phosphorescence caused by individual organisms disturbed by ship movement. The crucial difference lay in scale. While conventional bioluminescence appears in isolated points or narrow wakes behind ships, milky seas covered the entire horizon uniformly, creating the sensation of sailing over a continuous, unbroken luminous surface. Bioluminescent bacteria, microscopic organisms capable of producing light through internal chemical reactions involving an enzyme called luciferase, normally exist dispersed at low concentrations throughout the ocean water column. To generate visible luminosity on such a vast scale, these bacteria would need to aggregate at extraordinarily high densities, synchronizing their light emission in a coordinated way. Scientists specializing in marine microbiology are investigating chemical communication mechanisms between bacteria, a process known as quorum sensing, through which bacterial populations coordinate collective behaviors once they reach a sufficient critical population density. The proposed association between luminous bacteria and microalgae blooms is based on observations that organic matter released by decomposing algae provides an abundant nutritional substrate for explosive bacterial growth. Algal blooms, a relatively well-documented phenomenon in oceanography, occur when temperature, light, and nutrient conditions favor rapid multiplication of phytoplankton populations. When these blooms decline, they release organic compounds that could sustain bacterial population growth sufficient to create conditions favorable to the luminous phenomenon observed in milky seas. Satellite detection has become a valuable tool for documenting the extent and duration of these events, supplementing sporadic sailor reports with systematic data on coverage area and precise geographic location. Nighttime images captured by orbital sensors sensitive to visible light have, in some cases, revealed luminous oceanic patches visible from low orbit, demonstrating the truly continental scale some of these events can reach. This orbital perspective, unavailable to historical observers limited to sea level, has significantly expanded scientific understanding of the phenomenon's true magnitude. The Ganesha sailing expedition represented an important methodological milestone by combining direct observation with rigorous photographic documentation and water sample collection during the crossing through the luminous event. The crew recorded specific environmental conditions, including temperature, salinity, and the biological composition present, providing a valuable dataset for subsequent laboratory analysis. Samples collected allowed for identification of the bacterial species present, although a definitive correlation between the observed composition and the exact mechanism behind the collective luminosity remained incomplete even after detailed analysis of the collected material. The compilation of the database published in 2025 brought together hundreds of historical reports, ranging from old maritime records to recent satellite-documented sightings, creating an unprecedented resource for statistical analysis of the phenomenon. For the first time, researchers were able to examine seasonal patterns, preferential geographic distribution, and possible correlations with regional oceanographic conditions such as surface temperature and prevailing ocean currents. This systematic approach replaced a previously fragmented methodology based on isolated cases with no possibility of robust comparative analysis between distinct events. Geographic distribution revealed a preferential concentration in certain ocean regions, particularly near the northwest Indian Ocean, suggesting that specific environmental conditions of those waters are favorable to the development of the phenomenon. Factors such as proximity to upwelling zones, where deep, nutrient-rich waters rise to the surface, may contribute to conditions favorable to both algal blooms and the subsequent explosive bacterial growth. Statistical correlations, while suggestive, still don't establish a definitive causal mechanism capable of precisely predicting when and where the next events will occur. The central question that remains without a complete answer involves the precise synchronization mechanism that allows individual bacteria, each producing tiny luminosity on its own, to coordinate on a scale sufficient to create a unified visual effect spanning such an extensive area. Hypotheses involving chemical communication through specific signaling molecules offer a plausible explanatory path, but experimentally replicating the conditions needed to fully validate this mechanism in the lab presents considerable challenges, given the difficulty of simulating the scale and environmental complexity characteristic of the natural events observed in the open ocean. Future research will likely combine continuous satellite monitoring with targeted oceanographic expeditions, leveraging alerts based on patterns identified by the newly compiled database to position scientific teams during active events. This approach would allow for real-time data collection during the phenomenon itself, rather than retrospective analysis based on samples collected after the event has already partially dissipated. A complete understanding of Milky Seas will continue to require scientific patience, given the unpredictable and remote nature of these luminous events that periodically light up vast stretches of the nighttime ocean. Dark oxygen. Oxygen production without sunlight on the ocean floor. In July 2024, an international team of researchers published a finding that contradicts a principle considered established for more than a century: that all of the planet's free oxygen comes from photosynthesizing organisms, which need sunlight. Researchers discovered that metallic minerals on the deep ocean floor produce oxygen, at 4,000 meters below the surface. The discovery challenges long-held assumptions that only photosynthetic organisms, such as plants and algae, generate Earth's oxygen. The researchers wondered whether polymetallic nodules on the deep ocean floor generate enough electricity to produce oxygen through a process called seawater electrolysis. The discovery sparked immediate controversy. Critics published an opinion piece arguing that the oxygen production is likely an experimental artifact, resulting from trapped oxygen bubbles that gradually dissolved inside the measurement chambers. The scientific debate remains open, with no consensus on whether rocks on the ocean floor actually produce oxygen without light. Polymetallic nodules, rounded rock formations that slowly accumulate on deep ocean floor sediments, grow through an extremely slow geological process, depositing mineral layers over millions of years. Composed mainly of manganese, iron, nickel, and cobalt, these nodules are drawing growing economic interest due to industrial applications of these metals in batteries and electronics. The Pacific region, known as the Clarion-Clipperton Zone, where the research was conducted, contains a particularly dense concentration of these formations, making it simultaneously a target of scientific interest and potential commercial mining. Electrolysis, a chemical process well established in laboratories and industrial applications, involves splitting water molecules into hydrogen and oxygen through the application of electric current. Normally, this process requires an external, controlled energy source, such as batteries or generators. The revolutionary hypothesis proposed by the researchers suggests that polymetallic nodules could function as natural geobatteries, generating enough electrical potential difference to drive spontaneous electrolysis of the surrounding seawater, with no need for any biological intervention or conventional external energy source. Field measurements, conducted using experimental chambers positioned directly on the ocean floor at extreme depths, recorded a measurable increase in dissolved oxygen concentration over the course of the observation period. This result surprised researchers who had expected oxygen consumption due to respiration by organisms present in the sediment, not a net additional production. Repeating the experiment at multiple locations and at different times reinforced the team's initial confidence in the robustness of the observed phenomenon. Before the results were submitted for peer review and subsequent formal scientific publication, the electrical potential needed for saltwater electrolysis is theoretically close to 1.5 volts. Researchers measured voltages on the surface of individual nodules approaching that threshold, lending physical plausibility to the proposed hypothesis. The suggested mechanism involves electrical charge gradients formed by the uneven distribution of metallic elements within the nodule's mineral structure, creating a configuration similar, in principle, to that found in simple electrochemical cells used to generate electric current in conventional technological applications that have been known for decades. The implications of this discovery, if definitively confirmed, would extend far beyond an isolated geochemical curiosity. The current understanding of the origin and evolution of Earth's atmospheric oxygen is fundamentally based on the photosynthetic activity of ancestral cyanobacteria, a process that would have gradually transformed the primitive atmosphere's composition over billions of years. The existence of an alternative geological mechanism capable of generating oxygen independent of sunlight would raise relevant questions about whether similar processes may have contributed, even modestly, to the planet's complete geochemical history. Critics of the discovery raised specific methodological concerns related to the experimental design used. The main argument suggests that the measurement chambers, when sealed hermetically over marine sediment, could trap microbubbles of oxygen previously formed through conventional biological processes occurring near the ocean surface, later transported to the depths through currents or other physical mechanisms. Gradual dissolution of these trapped bubbles within the closed experimental environment could produce an apparent increase in oxygen concentration, mimicking a result that was interpreted as active production by the nodules. The original team responded to the criticism by presenting additional data and methodological refinements, including extra experimental controls designed to rule out the alternative explanation proposed by the critics. The subsequent scientific debate involved multiple detailed technical publications, with each side presenting distinct statistical analyses and interpretations of the same raw datasets available. This type of controversy, while it might seem indicative of scientific weakness to outside observers, represents the normal, healthy functioning of the scientific validation process when faced with a potentially paradigm-shifting discovery that challenges previously established consensus. The broader scientific community has adopted a stance of constructive caution, acknowledging both the evident methodological rigor in the original work and the legitimacy of the concerns raised by the critics. Independent replication by teams not involved in the original research has become a recognized priority, although the logistics of conducting experiments at extreme ocean depths make this process significantly slower and more costly compared to the typical replication of conventional laboratory experiments carried out under controlled, easily accessible terrestrial conditions. The practical implications of this scientific controversy also extend to regulatory debates over polymetallic nodule mining in international waters, an economically attractive activity that's potentially disruptive to deep-sea ecosystems still poorly understood. If dark oxygen production is eventually confirmed, and shown to be ecologically significant. Sustaining organisms adapted to this alternative oxygen source in sunlight-free environments. Arguments for protecting these geological formations would gain additional scientific grounding relevant to international discussions on regulating extractive activities in deep ocean territory that remains largely unexplored. Rogue waves, walls of water that appear out of nowhere. For centuries, sailors have reported gigantic waves appearing in the middle of a relatively calm sea, capable of sinking ships and destroying entire oil platforms. Science treated these reports as exaggeration or legend. Distinct from tsunamis, rogue waves are large, unpredictable surface waves that can be extremely dangerous to ships and isolated structures. On January 1, 1995, a monstrous 24-meter wave in the North Sea struck the Dropner oil platform, crushing steel railings and hurling heavy equipment across the deck. It was the first time a rogue wave had been measured in the open ocean. Recent research shows that these extreme waves don't need any mysterious forces to form. They emerge when common ocean wave behaviors, such as alignment and nonlinear stretching, converge at the wrong moment. The basic physics behind the phenomenon only began to be understood in 2025, 30 years after the first instrumental recording. Historical accounts of anomalous waves fill maritime records going back centuries, often described by survivors as walls of water rising abruptly amid moderate sea conditions, with no perceptible warning. Ships disappeared mysteriously, leaving few traces and no witnesses able to explain the exact circumstances of the wreck. Marine insurance companies, for decades, classified such losses as the result of navigational error or structural failure, refusing to accept an explanation involving a single wave of extraordinary magnitude, a phenomenon considered statistically improbable under the oceanographic models prevailing at the time. The dominant mathematical model for much of the 20th century, based on linear Gaussian statistics applied to ocean wave height, predicted that extremely tall waves would be extraordinarily rare events, occurring perhaps once every 10,000 years at any given specific location. This theoretical prediction directly contradicted the accumulated reports of experienced sailors, creating tension between traditional empirical knowledge and prevailing formal scientific modeling. The absence of direct instrumental measurement prevented a definitive resolution of this discrepancy, keeping the debate on essentially speculative ground for decades. The Dropner platform, an oil extraction structure operating in the North Sea, routinely kept wave height measurement sensors installed for operational monitoring and structural safety. During a storm considered significant, but not exceptionally severe according to weather forecasts, instruments recorded a sudden rise in height that substantially exceeded the surrounding waves, reaching approximately 24 meters from trough to crest. This instrumental record provided, for the first time, unambiguous quantitative evidence confirming the real existence of a phenomenon previously relegated to the category of an unlikely maritime legend. The conceptual distinction between rogue waves and tsunamis represents a crucial distinction frequently confused by the general public. Tsunamis originate through massive water displacement caused by geological events such as undersea earthquakes, landslides, or volcanic eruptions, propagating across the entire ocean as an extremely long wave, relatively low in the open sea, but growing dramatically as it approaches shallow coastlines. Rogue waves, by contrast, form through the local dynamics of conventional wind waves and swell, with no need for a triggering geological event, arising and dissipating relatively quickly within a limited ocean area. Scientific research following the Dropner event intensified considerably, combining satellite observation, advanced computational modeling, and experiments in laboratory-controlled wave tanks. Scientists sought to identify precursor conditions capable of predicting the formation of these extreme waves, a process complicated by the inherently chaotic and multifactorial nature of surface ocean dynamics. Multiple competing hypotheses emerged over the following years, each capturing partial aspects of the phenomenon without offering a complete, unified explanation broadly accepted by the specialized scientific community. The concept of directional focusing, a mechanism through which multiple wave trains coming from different directions temporarily converge at the same spatial point, adding their individual heights together through constructive interference, became one of the central explanatory components. When distinct wave crests momentarily align, the result can substantially exceed the expected height of any individual wave on its own. This mechanism, while statistically rare at any specific point, becomes inevitable when considering the vast temporal and spatial extent of the global ocean, explaining why such events, though uncommon, occur more frequently than originally suggested by linear statistical predictions. An additional component involves nonlinear instability, technically known as Benjamin fire modulation, a process through which energy present in a wave field can progressively concentrate into a single wave at the expense of neighboring waves through nonlinear energy exchange during propagation. This mechanism naturally amplifies certain waves beyond what simple constructive interference alone would explain, contributing an additional component of unpredictability and extreme magnitude. The simultaneous combination of this process with favorable directional focusing creates conditions particularly conducive to the formation of extreme events. The scientific advance achieved in 2025 finally managed to integrate these distinct mechanistic components within a unified mathematical framework, capable of computationally reproducing observed statistics on the occurrence of extreme waves with substantially greater precision than earlier, fragmented models. This theoretical synthesis doesn't eliminate the fundamentally probabilistic component of the phenomenon, but it allows for considerably more precise risk estimates for engineers responsible for designing offshore platforms, vessels, and coastal infrastructure exposed to potentially extreme ocean conditions in certain specific geographic regions. Practical applications of this improved scientific understanding extend directly into contemporary naval and offshore engineering, influencing structural safety codes, operational protocols for vessels in adverse weather conditions, and early warning systems based on monitoring ocean conditions favorable to the formation of extreme waves. Researchers continue refining predictive models, incorporating data from next-generation satellites and expanded networks of instrumented ocean buoys, seeking to turn a historically unpredictable phenomenon into a manageable risk through the combination of fundamental physical understanding and the growing computational capacity available for advanced oceanographic modeling. The 52 Hz whale, the only voice at its frequency in the ocean. In 1989, U.S. Navy hydrophones, originally used to track Soviet submarines during the Cold War, picked up a whale song at a frequency never before recorded. Its frequency of 52 Hz is much higher than the typical 10 to 39 Hz range of blue whales. The whale itself has never been spotted. It has only been heard through hydrophones, but its call has been detected since the late 1980s, in a pattern that matches the migration of blue whales and fin whales. No other whale has ever responded to its call. If it's a hybrid of a blue whale and a fin whale, it could have a lifespan of 70 to 90 years, meaning it could still be alive today. The hybrid hypothesis is the most widely accepted one currently, but it remains unconfirmed. No one has ever spotted or genetically identified the animal making this sound. The hydrophone system responsible for the initial detection was part of a military network called SOSUS, installed strategically throughout the Atlantic and Pacific during decades of geopolitical tension between world powers, originally meant to identify submarine movement through characteristic acoustic signatures. After this system was partially declassified for civilian scientific use in the early 90s, researchers gained access to an extensive archive of accumulated recordings, allowing retrospective analysis that revealed a completely anomalous sound pattern, recurring consistently across multiple monitoring stations going back to a period before the declassification itself. Vocalizations of blue whales and fin whales, species among the largest ever to exist on the planet, follow frequency patterns relatively well documented by marine bioacoustics, typically falling within specific low-frequency ranges associated with body size and the anatomical structure of these species' vocal apparatus. A frequency of 52 Hz, though still audible to the human ear only as a low hum, sits distinctly above these conventional ranges, creating an acoustic mismatch that would theoretically prevent the call from being recognized by individuals of neighboring species accustomed to processing signals within different frequency parameters. Tracking over subsequent decades made it possible to map this solitary individual's approximate migratory patterns, revealing seasonal movement consistent with known routes of blue whales and fin whales through the Pacific Ocean. This behavioral correspondence, while not definitively proving a specific biological identity, strongly suggests the animal belongs to some species of baleen whale, ruling out more speculative hypotheses involving a purely acoustic anomaly disconnected from any real living organism. The movement pattern has remained relatively stable, suggesting regular migratory behavior typical of baleen whales. The hybrid hypothesis, combining genetic ancestry from blue whales and fin whales, has gained partial scientific support through independently documented cases of natural hybridization between these two species in other populations around the world. Interspecies crossbreeding, though uncommon, occurs occasionally when geographic distribution ranges overlap during the breeding season. Hybrid offspring can display anatomical and physiological characteristics intermediate between the parent species, potentially explaining both the atypical vocal frequency and the possible difficulty in effectively communicating with individuals of either pure species. The impossibility of definitive genetic identification stems directly from the nature of the detection method used. Hydrophones capture exclusively acoustic information, with no possibility of collecting the biological material needed for DNA analysis. Visually locating this specific individual amid the vastness of the ocean, considering that even known, numerically larger whale populations prove extremely difficult to spot consistently, represents a monumental logistical challenge that no scientific expedition has managed to overcome to this day, despite occasional coordinated attempts by research teams interested in the case. The complete absence of any vocal response from other whales over more than 3 decades of monitoring is a particularly intriguing aspect of the phenomenon. Communication between baleen whales typically involves reciprocal vocal responses when individuals find themselves within mutual acoustic range. The persistent silence of potential interlocutors suggests genuine social isolation, either because the unusual vocal frequency truly prevents recognition by other whales, or because the animal's migratory path rarely places it close enough to other individuals to allow for meaningful acoustic interaction. An estimated lifespan of between 70 and 90 years, based on known data on the longevity of adult blue whales and fin whales, supports the real possibility that the animal first detected in 1989 remains alive today, given that detections have continued to be recorded in subsequent decades up to a relatively recent period. This potential longevity keeps ongoing scientific interest in the case alive, encouraging periodic renewal of monitoring efforts and acoustic analysis applied to more recent recordings captured by civilian and military hydrophone networks currently in operation. The cultural impact of this particular case has spread considerably beyond the boundaries of the specialized scientific community, becoming a popular symbol of loneliness and the search for connection. An emotional interpretation that, while understandable from a human perspective, lacks direct scientific support regarding any real subjective states actually experienced by the animal. Researchers specializing in cetacean behavior warn against excessive anthropomorphizing, noting that whale vocalization and social behavior patterns follow specific biological and ecological logics, not always directly translatable into human concepts of isolation or comparable emotional suffering. Continued scientific investigation depends fundamentally on maintaining and expanding ocean acoustic monitoring networks, a resource that faces constant budgetary and logistical challenges. Emerging autonomous hydrophone technologies, combined with increasingly sophisticated signal processing algorithms, offer the possibility of automated detection and real-time analysis of specific vocal patterns, potentially allowing for more precise identification of this singular individual's current location, should it still be alive, paving the way for eventual visual or genetic confirmation that would definitively resolve a mystery maintained over more than 3 consecutive decades of scientific observation. Mass strandings. Healthy cetaceans that throw themselves onto shore for no apparent reason. Periodically, entire groups of whales or dolphins, sometimes dozens of individuals, strand simultaneously on beaches, even while seemingly healthy. Among coastal strandings, however, no single cause explains the phenomenon. Mass strandings of sperm whales remain peculiar and largely unexplained events. In one case studied in Italy in 2009, 7 male sperm whales stranded along the Adriatic coast. Complete necropsies, including histopathology, virology, bacteriology, parasitology, and toxicology, were performed without identifying a conclusive cause. Potential causes that were ruled out or considered highly unlikely included infectious disease, gas embolism, vessel collision, accidental bycatch, predator attack, exposure to chemical or algal toxins, and abnormal weather conditions. Geomagnetic interference, military sonar, and navigational error caused by acoustic reflections in bays remain hypotheses under investigation, without definitive confirmation. Historical documentation of mass strandings dates back centuries, recorded even in ancient texts from coastal civilizations that occasionally witnessed dozens of large marine mammals appearing simultaneously on beaches, a phenomenon striking enough to merit written record during periods when systematic documentation of natural events was uncommon. The persistence of this phenomenon across different geological and oceanographic eras suggests a cause, or set of causes, related to intrinsic biological characteristics of certain cetacean species, particularly those with strong social organization in cohesive groups. Sperm whales, a species frequently involved in mass stranding events, are characterized by a complex social structure built on close family bonds and extensive cooperative behavior among group members. A behavioral hypothesis suggests that when a leading individual or significant group member becomes disoriented, sick, or in distress, the rest of the group may follow that individual toward shore due to strong social bonds, resulting in a collective stranding even when most of the animals remain physiologically healthy right up until the moment immediately preceding the event itself. The detailed necropsies conducted in the 2009 Italian case represented an exceptionally rigorous investigative effort, employing multiple scientific disciplines simultaneously to exhaustively examine possible pathological causes. Histopathology examined tissue at the microscopic level looking for signs of cellular disease. Virology and bacteriology investigated the presence of infectious pathogens. Parasitology looked for significant infestations. Toxicology analyzed the presence of harmful chemical substances in the animals' bodies. The lack of a conclusive finding in any of these areas, despite such comprehensive investigation, reinforces the likely multifactorial complexity of the phenomenon. The hypothesis involving geomagnetic interference is based on the known ability of various cetaceans to use Earth's magnetic field as a navigational tool during long-distance migrations, a biological mechanism not yet fully understood, but widely documented across various animal species. Localized magnetic anomalies, occurring naturally in certain coastal geological formations, could theoretically confuse these animals' navigation system, leading them to misinterpret a safe direction, resulting in a fatal approach toward shallow waters where stranding becomes physically inevitable due to insufficient depth. Military sonar, a technology used by navies around the world for submarine detection and underwater mapping, employs high-intensity sound waves that, according to several correlational studies, can coincide in time with certain stranding events recorded in different ocean regions. The proposed mechanism suggests that exposure to these intense acoustic signals could cause disorientation, panic, or even direct physiological damage to these animals' auditory and balance systems, leading them to seek shallow water as a behavioral escape response. Although a statistical correlation doesn't necessarily establish a direct, scientifically proven causal relationship, the specific coastal topography of certain regions, particularly bays with a gradually sloping shape and a soft sandy bottom, appears disproportionately represented among locations where mass strandings have repeatedly occurred over decades of observation. The navigational error by acoustic reflection hypothesis suggests that the echolocation system used by toothed whales to map their surrounding environment through their own biological sonar could malfunction in these specific seafloor configurations, generating confusing or insufficiently clear echoes that mask the real proximity of shallow water until it's too late for effective behavioral correction. Social stress and group behavior represent an additional factor frequently considered in more recent analyses of these events. Highly social cetaceans, especially species that travel in large, cohesive groups, may show increased vulnerability to mistaken collective decisions compared to more solitary species. Once the stranding process begins, even if it initially affects only one or a few individuals, distress signals emitted by these animals can attract and disorient additional group members, amplifying the scale of the event through an essentially social mechanism rather than a single environmental cause affecting all individuals simultaneously. Considerable variability among different stranding events documented around the world strongly suggests that multiple distinct causes, possibly acting alone or in combination, can produce a similar end result. This causal heterogeneity significantly complicates scientific efforts to develop a unified explanatory model universally applicable to all recorded cases. Specialized researchers recognize the need to analyze each event individually, considering geographic context, the species involved, specific environmental conditions, and the known behavioral history of the affected population before proposing a tentative explanation for any particular occurrence. Contemporary research efforts increasingly focus on preventive monitoring, using satellite tracking technologies applied to individuals from known vulnerable populations, combined with early warning systems that could theoretically allow for human intervention before the stranding process fully completes. Specialized rescue teams have developed refined protocols to help stranded animals safely return to deep water when intervention happens in time, although the success rate remains variable depending on factors such as elapsed time, the animal's physical condition, and the specific characteristics of the coastal terrain involved in each rescue situation. The song of the humpback whale, communication without a fully understood purpose. Humpback whales sing like poets of the ocean, filling the water with complex melodies. No one can say for certain why. Some think the songs attract mates, others believe they help whales orient themselves. What is certain is that these calls travel impressive distances underwater. hundreds, sometimes thousands of kilometers. The songs have structure, phrases that repeat, evolve over months, and are shared across entire whale populations that have never physically encountered one another. A cultural pattern transmitted across the ocean, without researchers fully understanding the mechanism of transmission or the ultimate purpose behind the song's complexity. The hierarchical structure of humpback whale songs has been systematically documented by researchers through decades of continuous acoustic observation, revealing a surprisingly sophisticated organization comparable, in certain structural respects, to formal musical compositions. Individual sound units combine into short phrases, which in turn group together into more extensive themes, eventually forming a complete song that can last between 10 and 30 minutes before cyclically repeating. Singing males often repeat this entire sequence continuously for hours, in some documented cases for periods exceeding 20 consecutive hours during a specific breeding season. Only male humpback whales produce these complex, structured songs, an observation that initially drove the hypothesis of a function primarily related to reproductive behavior, either directly attracting receptive females or establishing competitive hierarchy among rival males through a vocal display of physical fitness. The temporal pattern of occurrence, concentrated predominantly in tropical waters during the mating and breeding season, reinforces the association with a reproductive context, although occasional observations of singing during migration and in feeding areas complicate a purely reproductive interpretation as a complete and exclusive explanation for the behavior. Acoustic propagation in the ocean environment allows these vocalizations, produced at relatively low frequencies, to travel extraordinary distances through the same sound channel mechanism that enables the long-range propagation observed in other marine acoustic phenomena. Tracking studies using strategically distributed hydrophone networks have confirmed that individual songs can be detected by equipment positioned hundreds of kilometers from the original source, suggesting that the communicative function of these vocalizations could, theoretically, reach a potential audience spread across a vast oceanic area, far beyond what initial intuition would suggest possible for conventional biological communication. The most intriguing characteristic documented by researchers involves the consistent temporal evolution of songs within specific populations. Rather than remaining static, the complete melodic structure gradually transforms over months and years, with new elements being progressively introduced while old patterns are abandoned, a process researchers compare, with caution regarding excessive anthropomorphizing, to cultural transmission phenomena observed in human communication systems. The entire population of males within a given ocean region tends to adopt the updated version of the song nearly simultaneously, a synchronization that remains partially unexplained. The exact mechanism through which melodic innovations spread and are collectively adopted by an entire population of males, many of whom never physically interact with one another during the relevant period, constitutes a central question still without a definitive answer. Proposed hypotheses include learning through indirect acoustic exposure during periods of migratory overlap between different population subgroups, a process that would allow gradual dissemination of vocal patterns through an indirect chain of transmission, conceptually similar to how human cultural innovations can spread through social networks without direct contact between all individuals involved in the pattern's final adoption. The spatial orientation hypothesis, while less widely accepted than the reproductive explanation, has received renewed scientific attention based on observations suggesting a possible correlation between specific song characteristics and the acoustic properties of the surrounding ocean environment. Proponents of this hypothesis argue that the reverberation and echo produced by the vocalization itself could provide useful information about underwater topography, water depth, or the presence of obstacles, functioning as a rudimentary form of long-range echolocation complementary to other sensory systems already known and documented in this baleen whale species. The structural complexity of the songs, significantly exceeding what would be strictly necessary for simple functional communication, such as signaling presence or reproductive availability, intrigues researchers interested in broader questions about cognition and complex behavior in cetaceans. Some scientists speculate that the extreme elaboration observed could reflect a sexual selection process analogous, in general terms, to that observed in certain songbird species, where vocal complexity serves as an honest indicator of the singing male's genetic fitness or cognitive capacity for females evaluating potential reproductive partners available within the population. Comparative studies between different geographically isolated humpback whale populations distributed across different oceans around the world have revealed that each population maintains a song repertoire distinctly different from the others, while sharing general underlying structural organizational principles. This regional diversity, maintained consistently across generations within each specific population while evolving internally in its own independent way, suggests a robust cultural transmission system operating within relatively well-defined population boundaries, rarely crossing between groups separated by substantial oceanic distances. Contemporary research on humpback whale song increasingly benefits from long-duration underwater recording technologies combined with computational algorithms for acoustic pattern analysis, allowing for the processing of data volumes far greater than what traditional manual analysis could handle. These tools have revealed additional nuances in the structure and evolution of the songs, even as the fundamental question about the complete biological purpose and the precise mechanism of cultural transmission between distant populations continues to represent an active frontier of investigation within contemporary marine bioacoustics, territory where scientific understanding remains incomplete despite decades of dedicated observation and carefully accumulated documentation. The ocean floor remains Earth's least mapped territory. Only 26% of the ocean floor had been mapped at high resolution as of 2024. The bloop, attributed to ice fractures, still puzzles acousticians because of the sound's duration and pattern. Julia falls into the same category. Milky seas have a proposed bacterial explanation, but the mechanism that makes billions of microbes glow and sink, covering areas the size of entire states, still lacks a complete answer. Dark oxygen, discovered in 2024 at 4,000 meters of depth, divides the scientific community between historic discovery and experimental artifact. Rogue waves only began to be physically explained in 2025, 30 years after the first instrumental recording. The 52 Hz whale keeps singing alone, with no one having confirmed its species. Mass strandings of healthy cetaceans keep occurring with no single identified cause. And the song of the humpback whale, which crosses entire oceans, remains partially misunderstood even after decades of recordings and study. The ocean covers 71% of the planet's surface, and most of it remains the least explored, least mapped, and least understood place on Earth. Bringing these phenomena together reveals a recurring pattern in contemporary ocean research. Advanced instruments capture precise data, but full interpretation lags behind, requiring additional years or decades of analysis. Hydrophones recorded the bloop and Julia decades ago. The proposed explanations remain plausible, not definitive. Satellites have documented milky seas from orbit. The exact bacterial mechanism is still under investigation. Experimental chambers measured oxygen at 4,000 meters. Debate over the validity of the result remains active among experts. Each case shows that data capture frequently precedes, often by a wide margin, full scientific understanding of the observed phenomenon. The technological limitations of bathymetric mapping illustrate the scale of the remaining challenge. Covering the remaining 74% of the ocean floor at adequate resolution would require, according to estimates from international projects like Seabed 2030, continued investment of substantial resources over multiple additional decades. Each new sonar technology, each improved autonomous vehicle, adds a modest fraction to accumulated knowledge, but the vastness of the territory still pending guarantees that future generations of oceanographers will inherit significant work still to be completed in this monumental underwater cartography. The rogue wave cases show just how much time can separate initial observation from mature physical understanding. 30 years passed between the instrumental recording at the Dropner platform and a mathematical synthesis capable of integrating directional focusing and nonlinear instability mechanisms into a coherent model. This gap doesn't reflect scientific negligence, but the genuine complexity of multifactorial phenomena occurring within a chaotic system like the open ocean. A similar pattern may apply to the other cases. Explanations that are currently partial may mature through additional decades of data collection and gradual theoretical refinement. Cases involving cetaceans, the 52 Hz whale, mass strandings, humpback song, share a common methodological challenge. Living mobile organisms spread across a vast ocean resist the kind of direct, systematic observation that other natural sciences can more easily apply to confined terrestrial systems. Tracking a specific individual, capturing the exact moment of a stranding, or fully documenting cultural transmission of a vocal pattern between distant populations requires observational patience stretched over years, combined with considerable luck regarding equipment placement at the right time and place. The controversy surrounding dark oxygen illustrates the healthy, if uncomfortable, dynamic of scientific validation in the face of a potentially paradigm-shifting discovery. When a result contradicts a principle established for more than a century, the exclusively photosynthetic origin of atmospheric oxygen, rigorous scrutiny becomes proportionally intense. The debate between the original team and methodological critics doesn't indicate scientific failure, but rather the expected functioning of a process that requires independent replication and careful analysis before an eventual consensus is established, a process that can stretch on for additional years of cross-checking investigation. Financial and technological resources dedicated to ocean exploration remain disproportionately smaller compared to those devoted to space exploration, despite the ocean's physical proximity and its direct relevance to climate systems, biodiversity, and planetary resources. This investment disparity contributes directly to the slow pace of mapping and investigation seen in cases like those described here. Oceanographic researchers frequently point to this asymmetry when requesting expanded funding, arguing that the entire territory remains less understood than the lunar surface, despite literally being beneath the surface of the very planet we inhabit. Emerging technologies promise to gradually accelerate this pace of discovery. Artificial intelligence applied to processing large volumes of acoustic and image data makes it possible to identify patterns previously imperceptible through traditional manual analysis. Autonomous vehicles capable of operating for extended periods without constant human supervision expand geographic coverage capacity. Miniaturized, more affordable sensors enable deployment at a scale previously unfeasible. Each incremental technological advance brings the scientific community closer to filling the gaps that cases like the Bloop, Milky Seas, and Humpback Song currently leave open. The interconnected nature of these mysteries suggests that advances in one area frequently benefit research in others. Refinement of hydrophone networks, originally motivated by interest in whale vocalizations, simultaneously improves the ability to detect and analyze geological sounds like those attributed to ice fractures. Advances in bathymetric mapping aid both understanding of topography relevant to rogue wave formation and identification of potential habitats for species not yet cataloged. Investment in any front of ocean research tends to generate spillover benefits for related investigations, even ones that appear distinct at first glance. What remains, at the end of this review of documented but incompletely explained phenomena, is the recognition that 71% of the planet's surface hides, beneath layers of water and darkness, physical, chemical, and biological processes that defy simple categorization and immediate definitive answers. Every sound captured, every particle measured, every wave recorded, and every song recorded represents a fragment of a much larger mosaic, whose complete picture continues to be gradually reconstructed through increasingly sensitive instruments, increasingly sophisticated analytical methods, and successive generations of researchers willing to investigate territory that, despite covering most of the planet, remains consistently less understood than many distant celestial bodies observed through telescopes.